Hello, and thank you for joining me today. This is a kind of a special presentation we're going to be delivering today. We're going to be taking a look at Global Mapper within the context of a specific industry. As you can see on the screen, we're going to take a look at wind power development. One of the themes we're looking at throughout the month of August is alternative energy applications for Global Mapper, and we're hearing a lot from the users of our software as to how the tools and the components of the application can be used in very specific situations, solar applications, hydropower applications, and indeed wind power applications as well. So what we thought we'd do today is just take a quick look at some of the key components of the application and how they would apply in the development of wind power. We're going to begin at a macro level, a high level if you like, taking a look at some of the available data, some of the available resources that can be imported into Global Mapper, and we'll then kind of move down to a more local context and go through a simulated wind power development project. Now I have to say, by way of disclaimer, I'm not in the wind power industry myself, but just through conversations with our customers, conversations with our users, we're getting an idea as to the appropriate functionality in Global Mapper and how it pertains to that particular industry. So I'll simulate that, and I'll show you some of the tools in Global Mapper that you may apply for wind power development. So as I mentioned, we're going to start at a high level. We've got a map on our screen right now. This is a map of the state of Maine, where we are right now. And we want to take a look at some of the wind resource information that's readily available. There are data sets that you can download, specifically if you go to the website within the US of the National Renewable Energy Lab, NREL. You can access wind resource data that will give you an indication as to the potential for the utilization of wind power for electrical generation. Now that data, I've just got a sample of some of that data. I'm just going to turn on that layer. This is the data in its raw form. This is, again, freely available. I downloaded it directly from the NREL site, and this is what it looks like. Now we can do a lot of things with this data. I can use my info tool and I can select one of the polygons to determine the applicability. I think I choose one of the larger polygons. Let me choose a little smaller here. And you can see it has a factor of 2. This is a relative scale indicating wind power potential. We could also run our query function if necessary and build a query. Let me bring this dialog box down in size just a little bit. And we could build a query that, again, targets the specific areas that match our required potential. So for instance, if I wanted to find those areas that are greater than or greater than or equal to, let's do a value of 6. This scale, by the way, goes as far as 7 within this data. And we'll quickly run that query. And let's select all of those and quickly pull this out of the way. And you can see what we've done here is target very specifically within the state of Maine those areas that would represent the potential for maximizing the production of electricity as far as wind resources themselves. Now, obviously, there's a lot of other factors that will come into play, and we'll address those as we go through our specific scenario. Now, a better way of illustrating this particular data set is to apply a color scheme, if you like, develop a choropleth visualization, and that's what I've done right here. I've turned off the original data. Let me turn off my outline, leave my outline on for the time being, and let's turn on this the same data but with colors applied. I'm not going to go into the details of the procedure. This is something you can apply to any data within Global Mapper that has a variable of some sort. We can now represent that. I could, if necessary, put a legend on my screen to illustrate what those colors actually represent, but in this context that's not necessary because it's a relative scale. Increasing intensity of the implied color shows us where those areas of maximum potential are. And if I quickly zoom into let's say a little area in the center of the state here, you can see now the colors coming through. Red areas indicating those locations where wind energy is at its maximum, or wind energy potential is at its maximum. Now, to put this in a little context, we may want to add some additional data. I've got a couple of other layers here. We can throw in our county outlines. So if we want to, again, target a specific region based on counties, we can do that. And I've also got a layer that I've brought in the town boundaries for the state of Maine. So if I'm looking at developing wind energy in a particular geographic location, in a particular town, for instance, I now have the background data that shows me the potential, as well as the jurisdictional boundary, so I know where to target or where to to allocate my resources. So again, at a macro level, we can use this readily available wind resource data and essentially help us in our decision-making process as to where to target for this project we're working on. And moving down to a more local context, we can again bring in relevant data to help us in this process. What you're seeing on your screen right now, again, within the context of the US, we have this data available as a complementary or free data set. This is our NED data, our National Elevation Data Set. In the development of our wind power project, it is going to be important to factor in terrain, and you'll see that coming into play when we actually bring it down to a local context where we show the process of actually designing a wind farm, if you like. But as you can see, I've now rendered this terrain data on my screen. Where did I get this data? Well, this is available as an online streaming service in Global Mapper. Right here in the upper corner, you'll see this Connect to Online Data button, and you'll see options here for streaming data. These are categorized both geographically, US data for instance, as well as by theme. Now in this case, I'm going to choose terrain data, and you'll see a number of different options, some of which are US focused, some of are global. What I chose in this case was the 10-meter NED data. I was able to stream it into the application, in other words, show it in real time, and when I honed in on an area of specific interest to me, I was able to capture that, essentially export that to a local file, and that's what I have now. The file we're looking at is a Global Mapper grid file that I exported from that streamed data. It's now a file that's on my hard drive. So this gives us both a visual context and also a functional base for a lot of the processes we're going to follow in a few minutes. The other data set that I was able to access online is a land cover data set. Again, in the dialog box I just showed you, there's a section for land cover. And for this area, we have a raster representation of land cover. Now, land cover comes into play because it allows us to gauge the relative roughness of the terrain and ultimately its suitability for consistent wind and ultimately electrical generation. One of the options that we have, which is very specifically targeted to wind energy exploitation, is the generation of a roughness grid, which looks at this land cover data and comes up with a gridded layer that illustrates where the friction or roughness is likely to be less, again increasing the potential for efficient electrical production. The way this process works with my land cover layer, again locally saved from my streaming server, I have a local file, we can right click on that layer, and from our analysis menu, recognizing the format of data, it will give us the option to generate a roughness grid. Now I'm going to make sure I choose the right layer. It's my land cover layer. We'll click OK. And the roughness table can reflect one of the available formats of land cover data. The NLCD, National Land Cover Data Set, is a US data set, but you will notice other data sets are available globally as well. These again are available as streaming services, so if you're using, for instance, some of the other land cover data sets, you can make that decision here, which will allow the gridding process to be applied in an applicable way. So in my case, we'll leave it as is. We are creating a gridded layer from this process, so it's essentially going to give us a visual representation of relative roughness based on whatever shader that we have selected. Now, these are the same shaders that we will use for terrain. We'll address these in the context of looking at our terrain data in a few minutes. But here in the context of my roughness grid, I can choose which of these shaders to use, or indeed I can choose a custom shader. And I actually created one for this purpose. This is simply a single color for which I've applied different intensities. So I will quickly see from light color to dark color areas that are relatively rough and have less roughness, more applicability as far as wind power generation is concerned. So we'll use that custom shader. One of the options here, by the way, is also to create areas or polygons, vector polygons. I'm not going to do it in this case, but if you want to be able to interact with this roughness data, run a query perhaps, or look at potential sites that fall within areas of minimum roughness, you can absolutely generate these polygons as part of this process. I'm not going to do it in this case, we just simply want to see the results. So we'll click OK. And you'll see that we now have a new layer, a roughness grid layer, to which my custom shader has been applied, lighter colors, less roughness, darker colors, more roughness. Now here in the state of Maine, we're a heavily vegetated state. We've got a lot of trees. Trees tend to interfere with wind patterns, and you can see that represented here. These areas with heavy foliage have a higher relative level of roughness, so perhaps less potential for wind power generation. Open areas, again, open water for instance, open fields, you'll find that wind power generation is going to be much more optimized in those locations. So our roughness visualization will give us that regional perspective as to where would be the maximum, again, based on this data, where would be a maximum potential for wind power generation. So one of the things I want to do is identify within this localized area the linear feature that represents the ridge line. Now this is obviously the high point along a given area of terrain that will represent an optimal location for the actual placement of my wind turbines. There's a very, very useful tool in Global Mapper for performing that function. Very seldom used. Probably for those of you who have used Global Mapper, you may not even be aware that it's here, but from the analysis menu, find ridge lines. Now, functionally, this tool works just like our watershed tool. Those of you familiar with watershed analysis, watershed generation, the ridgeline tool works in virtually the same way, but in reverse. Instead of looking for areas where drainage would accumulate, it does the opposite. It looks for ridge lines. So it's an inverted watershed tool, if you like. Now, for this purpose, I'm going to define my cell count, which is basically my area, as 1,000 cells. Again, this is really out of context. This will be applicable more for watershed. Depression fill depth, again, inverted from what we use for watershed. I'm going to keep this fairly low. I'm going to use a 1 meter threshold here. In other words, areas that of my ridge that deviate beyond 1 meter will not be considered part of my ridge line. So we'll leave that at 1 meter. Again, the bounds, we're going to limit this in this case to just what's on my screen. Now, if everything goes according to plan, I should see delineated on the screen the ridge lines, or the high areas connected with a line feature. I'll click OK. And you can see that now throughout the area. There's a very distinct ridge line here. Some of the ridge lines may not be as apparent visually, but in the local context they represent high points of land. Now the specific area that I'm interested in is right in here. So what I'm going to do is use my digitizer. I'm going to select a number of these segments. I'm just literally clicking on those line segments with my mouse. I'm going to hold my control button down. I'm going to grab a few of these. I don't think I need that last one actually. Let's just grab this one, and perhaps the final section. Actually, we'll take that one out. I want to target very specifically this section. I think that's probably fine right here. So because this is multiple segments, in this case it's just 2 segments, what I'm going to do is combine them together, combine these lines. I'm going to right click. Because they're selected, whatever I choose from this list will be applied to the selected features. I'm just going to combine those line features. It gives me the option of a distance threshold, so that lines that are not abutting will actually connect. And this is at 10 meters in this case, which is probably fine. We'll click OK. We can also determine whether that connection is based on an attribute. Not relevant in this case. We'll leave that as is. And again, click OK. And from that line I've created, from those multiple lines, I've created one single line. Now, this is the only line that I want to retain. The other ridge lines I'm no longer interested in. Number of ways we can do this. The easiest that I find is just to copy that selected line, Control C on my keyboard, Control V. I'm going to paste it into a new layer. And we'll call this Wind Farm Ridge. Or we could give it a name if the actual wind farm proposed had a particular name. So that's now a new layer in my overlay control center, confirming the projection. The original ridge lines I'm no longer concerned about. And it's prompting me to move. I'll disable that. Use my digitizer. And you can see a little short section. I may have extended it to the end of the ridge, but that's fine in this case. But that line feature allows me to essentially delineate the high points, connecting the dots representing the high points. Now the next thing that I'm going to do is to determine the optimal locations for the actual wind turbines themselves. So with that line selected, one of the really useful functions is to generate point features. Now, I've gone to the advanced feature creation options, and you'll see here an option to create points from selected areas or lines. I don't have any areas, but in this case lines. There are actually two variations on this theme. One is based on the vertices. The other is for me to specify along that line where my points are going to be. And that's the option I'm going to use in this workflow. Couple of ways I can do this. I can either decide the spacing of the points that I'm going to generate, or I can decide how many I want. Now in this case, I'm going to choose that I want 10 wind turbines spaced along this ridge. So instead of doing a fixed distance, I'm going to do a count and simply type in the number 10. The option, which is checked by default, by the way, keeping all vertices, we want to uncheck that. We want to limit this just to 10. We do not need to apply a point where our original vertices are located. So with this, these settings applied, let me click OK, and you can see now the simulated location for my individual wind turbines along that ridge. Once again, I want to apply these to their own unique layer. So a couple of ways I can do this. I can edit them. I can right click and edit, or once again copy and paste. In this case, I'm going to edit because these points are inherently generic point features and not really what I want. I'm going to right click, I'm going to edit. And with those points selected, I can choose a number of settings. I can choose the feature type, I can choose the feature layer. In my case, I want to generate a new layer for those wind turbines. I want to have them in their own unique layer, and it will be named appropriately, as you'll see in a second. The other thing I want to do is I want to apply a feature type. Now, this is a little bit like a cooking show that I prepared earlier. I have a feature type called wind turbine. The wind turbine visual representation is a little dot, just like you see now. However, for the three-dimensional representation of the wind turbine, which we will see in a few minutes, I've actually assigned a three-dimensional model of a wind turbine, which is actually pre-configured in the software. I'll take a look at that in just a second, how I did that. But while we're here, I want to make sure that the assignment is correct. My feature type is wind turbine. Feature layer, as I mentioned, we'll create a new layer. And a few other settings in here. I could modify attributes if I wanted to. I could change the symbolization manually, but I'm going to use the default for what I've selected here. Everything else should be fine. When I click OK, I'm going to be prompted to name this new layer. I'm going to call this wind turbines. That contains the actual turbines themselves. And we'll click OK. Once again, confirming the projection. It's going to inherit the projection parameters from the display projection, so that's fine. Now, my user-created features layer, which is where they were before, I can remove that now. I don't need that anymore in my workspace. I don't need to save the workspace at this stage. So we now have individual wind turbines denoted by a number. We could change that obviously for each individual location if necessary, and obviously the indication of the locations are represented, and they are equally spaced, which is important as well. Now, as I mentioned, I was going to show you the previous work that I had done to generate that wind turbine feature. I want to show you in the configuration dialog box what I did. Under point styles, this is the feature I created, wind turbine. I designated a default symbol, which is again as a dot. You can customize that if necessary. But the important thing here is I also added a 3D model. Now, we're not seeing that obviously in the top-down view. We will in a few minutes. There are a number of pre-configured models you can see in here. Variations on trees, power poles have been added, hospitals, fire hydrants. We've used that one in a previous scenario. So for this particular feature type, I've designated a pre-configured model. We can also import your own, by the way. Under custom symbols, we have the option of importing our own 3D model if we have access to that. Now, the other thing I did for this feature type was I added a couple of attributes. We're basing this on the assumption that my wind turbines have a very specific size. So the attributes that I added, well, first of all, there's an elevation. Elevation is 0. The base of my wind turbines is always going to be on the ground. This is relative to ground, as you'll see. It will apply relative to ground in this case. The height of my wind turbines is noted here. Now, the reason I put this in, the reason I have to put this in, is this is going to to reflect the actual height of the model itself, or the relative height of the model within the 3D view. So 30 meters, that's consistent. You'll see these attributes, while they are editable, I've established a default value in this case. So every time I apply this feature type, it will inherit those characteristics. We'll click OK. Again, that's all has been done previously. And we will see the results of that as I mentioned just a minute ago. Let me turn off the ridge itself. It's served its function. We'll retain just the wind turbines themselves. And let's take a look at our 3D view so we can see those wind turbines themselves. Difficult to see. We're a little far away. Let's come in a little closer. And you can see now each of these points represented in my 3D view looks like a wind turbine. It actually looks like what it's supposed to represent. There's my ridge, clearly noted, and this is my simulated location of my wind turbines. We're going to come back and look at this a little bit later. We'll actually generate a little fly-through visualization as well. A couple of other things we need to do. Again, in the local context, there may be some engineering requirements. I want to show you in Global Mapper some of the tools that are available for doing some analysis of the terrain or some modification of the terrain. Now, for this, what I'm going to do is use my digitizer and select all of these points. Now, these obviously are specific points or specific locations. What I'm going to do now is actually generate a buffer around each of these points. We would assume that when we create our wind turbine, this is going to be a flattened area that we're going to have to generate in order to build on. So we're going to first of all generate some buffers. I'm going to right-click, or we could right-click and buffer, or there's actually a tool in the toolbar, I keep forgetting. We can use that. Define the buffer distance. Right now it's set to 20 meters. Well, that's probably fine. We'll leave that as it. Maybe bring it down to 10 actually. A little bit smaller. So 10 meters radiating out from each individual point will generate a new circular feature, if you like. And we just want one buffer for each feature. We could do concentric buffers if necessary, but that's fine for this in this situation. We'll click OK. And you'll see little rings. Now, once again, I'm going to copy these. I'm going to paste them, Control-C, Control-V. I'm going to create a brand new layer. And that layer is going to be called buffers. Because once again, it allows us the opportunity to keep our data organized, and we can, again, remove our user-created feature, which was initially used as the basis of that. So with my digitizer, deselect, and you can, if I zoom in close, you can see that concentric ring indicating the extent of the physical engineering that's going to have to be done at that site. Now, what I'm going to do is perform a terrain modification at a very local level for each of those circular features. Unfortunately, the source data that we're working with now is fairly low resolution. It's a 10-meter resolution data set, so I'm not really going to get the results that I need. So what I'm going to do instead is I'm going to bring in some LiDAR data. Now, for this particular project area, I was able to go to our online data once again. I was able to bring up the section on LiDAR, and I'm not going to go any further than this, but I was able to select, in the context of the US, once again, we have access to this US Geological Survey National LiDAR dataset. When I clicked the Connect button after selecting that option, it took me to the national map site and showed me for the area that I'm working in which LiDAR tiles are available. I've already done that. In fact, I've even cropped them down to a very localized area. I don't need the LiDAR data for anything beyond, but I have my LiDAR data, my point cloud data for my localized area. I'm going to use this to create a higher quality elevation data set to give me a much more precise terrain model for the area that I'm going to be engineering for this wind farm. Again, it's not relevant for me to generate the data at a wider level, but just for this local level, and you can see that's exactly what I've selected here. So how do I generate that grid? Very simple process. We're using our elevation grid button right here in the toolbar. We have a number of layers. I want to make sure we're not gridding our wind turbines or our buffers. We don't need that. Just our LiDAR layer. We'll click OK. And this is the grid generation dialog box. I'm not going to go into the details right now. This has been done in many previous workflows. I do want to make sure that when we grid this data, we're not using all of the points, but just those that represent ground. So we'll apply that filter. Everything else here should be fine. We'll click OK. And when the process completes, easier to see if I turn off the points, we now have a new, and you can see, much more precise terrain surface. The problem that you may encounter when you work with data like this, the transition between high quality and low quality data may be an abrupt drop off because we're dealing with something that's much more precise, much more reflecting the actual terrain. What is being displayed in the data behind is a much lower resolution data set. So to illustrate this, I'm going to use my profile tool. I'm going to quickly draw a cross-sectional view. And you can see right off the bottom of my screen here, quite an abrupt drop off here. So while my localized data is much more accurate, a much more accurate representation of the terrain, at that transitional point, it doesn't look too good. It looks like there's a bit of a cliff here. So the solution to that is to perform a process called feathering. And I'm going to feather the new elevation grid that I've just generated. Right-click on Options or double-click to bring up the Options dialog box, and you'll see feathering. Now, we've performed feathering in many of our presentations with imagery, for instance, where it'll feather maybe different resolutions of imagery together. We've worked with terrain. Typically, we'll do this based on a rectangular data set, but in my case this is not rectangular. This is based on a buffer around my wind project. So instead of buffering along edges, we're going to feather to the coverage area of what it sees in the data. So basically we use this option. We can also choose the pixel threshold that will feather. In other words, how much compromise do we want to apply? 100 pixels is fine in this case. We'll click OK. You will immediately see the visual results of this. It appears to kind of blend itself with the terrain data in the background. More importantly, it also will blend itself from a terrain perspective. You can see now what was an abrupt cutoff is now a smooth transition. So this gives us the benefit of having a high quality local elevation data set, but it doesn't look like it's detached from the original data we have underneath. It also allows us to use terrain data outside of the immediate vicinity or immediate area of our LiDAR data. That's of a lower resolution, but definitely very appropriate for just a broad regional view of the terrain. So as I mentioned, the intent of the buffering process was to allow me to create a locally modified terrain surface. So I'm first going to choose my buffers layer. I'm going to right click and I'm going to select all of those buffers. Now I can't really use the digitizer very effectively on the screen itself because it would obviously select more than just the buffers. It would select the points. So easiest way for me to select everything in a specific layer is right click and select all, as I mentioned. Now the process of generating this flattened surface that is going to be the basis for our engineering, and again, a two-step process. We're going to generate volumes, we're going to calculate volumes, and also generate a new surface. It's initiated through our cut and fill process. Right click, advanced feature creation options, and we have an option here to create a flattened site plan grid from selected areas. I have 10 areas selected on the screen, so each of these are going to be locally modified based on the inherent height within each of these polygons. And I'll use the heights that are in there. We could optimize or ask Global Mapper to optimize the cut and fill based on what it sees in the local area, but this would be the same for all, so that wouldn't work in this context. So I'm going to use the localized height that's applied to each polygon. Everything else here should be fine. We're going to have slopes that will integrate these individual terrain areas into the original terrain. We'll see the results of that in just a second. We'll simply click OK. So I'm going to go through a couple of individual calculations to determine the best possible height, if you like, and ultimately it will display for us the results as a calculated series of values. Shouldn't take too long, and there we go. You can see in order for me to flatten each of these 10-meter buffers or 20-meter diameter areas, I'm going to be required to move about just under 500 cubic meters cut volume, and I'm going to fill about 200 cubic meters. So a little bit of material needs to be moved around. This is great for our engineers. It tells us how much actual work is going to have to be done. If I click OK on this dialog box, the results of that are actually applied to the terrain. Now we're not seeing that at this level. However, if I zoom in a little closer, we should see a localized terrain surface, and the visual clue here is it's a solid single color as opposed to what you see in the surrounding terrain. Each of these is now a flattened area. I'll turn off the original buffers. They have served their function, and we'll see that again the underlying terrain. Probably the easiest way for me to illustrate this is to draw a profile that cuts through my site, and you'll see Where the original terrain noted in red was as indicated, the flattened area based on the inherent height is noted here. Now this is an exaggerated perspective, obviously. We don't have that much terrain variation, but it does illustrate the fact that each of these wind turbine sites now is a flat area, and that is now essentially burned into the terrain at the local context. So it gives us a more accurate model of what this would look like when we're finished with our project. Now, obviously, the site planning process is only stage one of the procedure. There's a few other things that we can illustrate here. Just very quickly, bringing in other layers that are relevant is one thing. Let me just zoom out just a little bit to give us a more wide area context. Let's see, I use my zoom out function. And this is where we started originally. You can see the localized area of high resolution terrain surrounded by our 10-meter data. A couple of the other layers I have in my workspace here. We've got our properties layer, and you can see the extent of our project and perhaps the impact it's going to have on the local area. One of the things that we could do is essentially buffer our wind farm, the extent of our wind farm, and determine those properties that are going to be impacted. I'm not sure if this is necessarily realistic. My location, this is obviously simulated, but if this was the case and we needed to get buy-in from local property owners, obviously that would be an issue. Or there may be easements that are required. Transportation is another one. We need to have access to the site. For that purpose, we may have to do some engineering for access for heavy equipment. Again, very quickly simulating how that process would work. We may be able to bring in, for instance, our road layer to see if there's any access already. Looks like we have a little road that terminates right here. And very quickly, I'm just going to draw a line, perhaps indicating where we might have our access road. Just a very simple line. I'm not even going to change the layering, but that may illustrate for us, or maybe reflect our access. Now, the really important thing about this is obviously the heavy equipment that has to be transported. We may need to see if that's applicable. So what I'm going to do is quickly select the line I've just drawn with my digitizer, and we're going to quickly profile it. We can actually generate a profile line to show what the terrain. You can see the localized high quality terrain as well, so we can gauge the steepness of the terrain to see if this is going to be suitable. So again, just another illustration of some of the other data that come into play with regard to this this project. Another layer that I have available, I'm not sure if I've actually loaded it here, is environmental. I don't actually have it in my workspace right now, but again, something that you could come into play. Maybe nesting sites or areas of environmental concern that may be impacted. Those data layers could be brought in as well to give you a broader picture of the impact of this project. Now, the final workflow we're going to go through, actually, I've got a couple, but the next workflow we're going to go through is a visualization or a modeling of the visual extent of this project. Now, I'm going to clean up my map just a little bit here. I'm going to turn off a few of my layers. I'm actually going to turn off the upgraded terrain layer. Let's turn off my property information on my roads as well. I'm not sure they're relevant in this case. And I'm once again going to zoom out just a little bit further than previously. Let's zoom out to the extent of this terrain data. And what we want to measure here is the visual impact of these wind turbines. I'm going to choose one of the wind turbines at random. It doesn't really matter which one, but that's going to become the basis of my viewshed analysis. A viewshed allows us to determine from a given location what can be seen, or the reverse. If we target a specific feature and we can determine the height of that feature, we can see from where this would be visible. I'm going to right click, or actually I'm going to choose the tool. I'm going to select on the map. Because it sees I have a point selected, one of my selected wind turbines, I will create a viewshed for that point. We'll click yes. And my viewshed parameters allow me to do things like to determine, normally in the context of transmission, it will allow me to determine my transmission elevation. In my case, this represents the height of my wind turbine, 30 meters, and that is above ground. So basically, I want to see where within the extent of my map view, or the extent of the radius I'm going to define, where I can see these wind turbines. Where is there going to be a visual representation of these turbines? And this is based on the assumption that somebody's going to be 2 meters above the ground, which is the average height of a person. This is going to give me a 360-degree view. We'll click OK, and we'll let this go, and when it finishes, we'll see the extent. So as you can see, the red area indicates where my wind turbines are going to be visible from. You can see it. Very few areas are not going to be able to see my project, my wind turbines. Areas that are not shaded red, obviously those are probably hidden behind terrain features, things like that as well. So another analysis function. Local community may be concerned about the visual impact, and you can see now that we have the option to generate an outline of that extent. Now the final component of Global Mapper that we're going to look at here, let me turn off a couple of layers here. We'll leave our wind turbines on. Don't need to have them selected. We can deselect, and let's zoom back into our local area. I will turn on my modified surface, my terrain surface, my elevation grid, and you can see noted right here. And we're going to generate a visualization of this project. Perhaps we want to share something with our constituents to show them what the project will look like. I'll also turn on my imagery. I think I have some imagery in my workspace. I may have to move a few layers around for it to actually be visible. There we go. Oh, I don't need let me move that imagery actually right to the bottom. That will be a little better. There we go. There's my imagery. You can see my wind turbines themselves. What I'm going to do is simply draw a line on the map. Now, this line is going to represent a flight path. It doesn't matter where I start. And indeed, the line itself doesn't have any specific characteristics of importance. I'm just going to fly along the length of my project. Very short line segment. Again, doesn't matter what the characteristics are, the feature type. I'm going to put this in its own layer. Let me go ahead and create a new layer, and we'll call this flight, so we know what we're dealing with. And click OK. Now, the process of transforming that line into a flight path requires me initially to select it and to use the flight parameters, a 3D fly through parameters dialog box, to determine what this flight will actually look like and how it will behave. Now, this is going to be something we will view in our 3D view, but the initial setup can be done here in the 2D view. What we have is a list of vertices along that line segment, my X and Y values. You'll notice the columns include Z, time, velocity, etc., which are not yet populated. When I establish the settings for this flight, those settings will be applied as well. I'm going to conduct a straight ahead flight. Fixed direction and fixed point are options here. I don't need to work on bank angle. We'll not do that in this case. Bank angle will allow me to essentially simulate what it will be like if you were actually in an aircraft. When you turn a corner, it would bank slightly, obviously. I want to determine an elevation. We can do this either based on ground or based on actual elevation. I'm going to base this on ground, relative to ground, and we'll keep this height. Our turbines are about 30 meters. Let's go for about 40 meters. The duration and the velocity are connected. Duration obviously reflects how long it'll take you to get from the start to the finish of your flight line. Velocity will be calculated based on that duration. You can edit either of those. It will impact the other. So for my duration, let's make this a fairly slow. I'm going to make this I'm going to make it 25 seconds. I'm going to take 25 seconds to get from the start to the end of my line. With those settings established, you then generate the fly-through data, which populates the table above. Each of these individual lines are now editable. So for this first flight segment, I can change the velocity. I could change the heading. I can change the pitch. Simply right-click or double-click and bring up the parameters for that segment. You may want to start this particular sequence a lot slightly higher. I'm going to start at 100 meters, allow me to kind of swoop in a little bit towards the first of my wind turbines. So at an individual level, you can be very specific. Now, again, these are reflecting individual vertices. If you want even more control, you can resample the line, add many, many more vertices, and edit them as needed. So you can really go to town in regards to the settings here. Again, everything else should be fine. We'll click OK. Nothing initially has changed in my 2D view. What I'm going to do next is pop up my 3D view to show a visual simulation of that flight. So the playback functions are controlled in several buttons in the toolbar, and we have the option to edit each individual frame. If we wanted to change the settings for each, we can play back, which we'll do in just a second. We can stop the playback, and ultimately when we're happy with the results, we can save the fly-through as a movie. There's a number of options as far as the movie parameters are concerned. Just as a final visualization, I'm going to hit the play button. And you can see, it's going to take a while just to render a little bit here, but you can see my visualization now flying through the area that I've designated as my wind farm location. Just taking a little bit of time here to fill in some of the terrain, but maybe I could have made this a little slower, it's a little fast. I could have weaved in and out of the wind turbines if necessary, but to share this information with stakeholders, to get buy-in from the community, it's a great visualization tool. Playing that back and seeing what that would look like. So those were just some of the functions that Global Mapper can be that are applicable for wind power development specifically. If you want to find out more about Global Mapper's functionality, we do have a series of webinars, webcasts that we record, we put on our YouTube channel. So go to our YouTube channel, subscribe, go to our website, you'll see them listed there as well. Thanks for joining me today.